The second law of thermodynamics makes a very clear and very grim promise to us all. Everything eventually decays. Because of entropy, every physical system naturally moves from a state of order to disorder, which means every machine, tool, and structure you have ever used is mathematically guaranteed to fail. But there are a few strange exceptions that seem to ignore this rule completely. Objects that survive extreme drops, heavy impacts, and decades of use without a single scratch. Mechanical engineering relies on a concept called infinite life. If you design an object so the stress stays entirely within its elastic limit, it can survive 1,000,000 cycles of use without permanently bending, a mechanical failure known as plastic deformation. These objects aren't breaking reality. Their designers simply found clever ways to use the laws of physics against themselves. When an object hits the hard ground, the kinetic energy from that sudden stop has to go somewhere. Most modern devices use rigid glues to hold everything tightly in place. The problem is, glue traps those kinetic shock waves inside the delicate components, tearing them apart. The Nokia 3310 was built differently. Instead of being glued shut, its internal components sit on spring connectors. When the phone takes a hard hit, it is designed to intentionally pop apart. This lets the kinetic energy safely escape outward as physical motion, rather than destroying the circuitry. Add in a shock-absorbing double plastic shell and a glass screen safely recessed below the outer lip, and you have a structure perfectly designed to take the hit before the fragile parts ever do. Duralax glassware uses a different strategy called thermal tempering. By cooling the outside faster than the inside, engineers lock the glass in a state of permanent internal compression. This microscopic tension allows the glass to absorb massive impacts that would shatter standard drinkware. Both methods solve the same problem: energy management. Indestructible objects survive by finding a place for force to live, either through physical motion or internal compression, rather than letting it shatter the structure. If we zoom down to the atomic level, we can see exactly why some materials snap while others bend. Ceramics have highly directional, rigid bonds. When stressed, they shatter. But metals have non-directional bonds, meaning their atoms can slide past one another. This happens through a mechanism called dislocation motion. When continuous stress is applied, a fault line in the atomic lattice smoothly shifts over by a single position along a slip plane. The grid deforms, but the overall structure stays intact. But this atomic flexibility has a limit. When liquid metal is poured into a mold to cast it, it cools into microscopic crystalline grains that point in random, chaotic directions. But under immense pressure, those random intersections become critical weak points. To fix this, engineers forge the metal. By crushing the solid material under immense physical pressure, they force the microscopic grain flow to align perfectly with the anticipated direction of stress. Forging transforms metal from a collection of random grains into a series of deliberate, load-bearing pathways. But even perfectly forged, completely atomically aligned metal will tear apart if its macroscopic shape is poorly designed. Engineers measure this using the stress concentration factor. It's a mathematical ratio proving that sudden geometric changes, like a drilled hole or an abrupt corner, exponentially amplify the physical stress in that specific spot. Early jet manufacturers learned this the hard way. Square window cutouts and sharp corners created intense stress spikes, causing airplane fuselages to literally tear open mid-flight. The same invisible killer affects large-scale infrastructure. Overly thin connection plates and unmanaged geometric stress points can fatigue for decades before causing a massive bridge to suddenly collapse. This heat map shows the remarkably simple solution. On the left, a sharp 90-degree angle forces stress lines to crowd together dangerously tight. On the right, adding a rounded edge, called a fillet, allows the physical force to flow smoothly and evenly. Eliminating sharp edges is the most critical design mandate there is. It keeps localized microscopic stress from triggering a macroscopic disaster. If an object can survive physical impact, atomic stress, and geometric fatigue, it still has to face the slow destruction caused by heat and time. Stanley thermoses defeat thermal entropy using a vacuum. By completely removing the air between their double steel walls, they eliminate the physical medium required for convective heat transfer, trapping the temperature inside. Cast iron skillets actually use heat and time to their advantage. When you bake cooking oils into the iron, the process of polymerization occurs. The oil molecules bond, flatten, and harden into a smooth, rust-proof shield that constantly heals itself every time you cook. The common instinct is to assume that making an object indestructible means making it completely hard, stiff, and rigid. But stiffness is exactly what causes materials to crack under pressure. The common thread across all these designs, from atomic slip planes to spring-loaded casings, is a refusal to resist force through sheer stiffness. Resilience depends on moving in harmony with physical forces. The universe guarantees that all things will eventually return to dust, but with brilliant engineering, we can push that expiration date so far into the future that, at least for a human lifespan, these objects are effectively immortal.